Hi everyone, welcome once more to this YouTube channel at Best Science Brain YouTube channel. Today we're going to have an online lecture on advanced organic chemistry, and today we're going to look at nucleophilic substitution reaction mechanism. Nucleophilic substitution reaction mechanism. So if you are seeing this video either for the first time, so you have to watch this video from the beginning to the end to understand the nucleophilic reaction mechanism, the SN1 and SN2 reaction mechanism to the end of it. So at the end of this video, you'll be able to solve problems involving SN1 and SN2 reaction mechanism. This is your online lecturer or teacher, Dr. B. If this video is meant for people in tertiary institutions, in the university, polytechnic, college of education, or those offering postgraduate studies in chemistry, organic chemistry precisely, or pharmaceutical chemistry. So this video is for you guys. So we're going to start. If you are not subscribed to the channel, kindly tap on the subscription bell, the pear-shaped bell, beneath the video as it's playing. Tap on it and get subscribed to the channel. Share videos to your fellow classmates and to other classmates or friends in tertiary institutions offering science courses, those in Skonye and those in postgraduate studies. So for them to understand and follow us in this video, we welcome every constructive criticism as we tend to improve better in this online tutorial work. So now, before we start, we have to first of all go through substitution reaction. We have already done that in our first video. When we did, remember that in our first video on organic reaction mechanism 1, this is reaction mechanism 2. So we introduced substitution reaction as a reaction that involves the replacement of an atom or group of atoms by another atom or group in a saturated organic compound. A reaction which involves direct replacement of an atom or group of atoms in a saturated organic compound by another atom or group of atoms. That's what is meant by substitution reaction. In organic chemistry, there are different kinds of substitution reactions. We have the free radical substitution reaction or mechanism, and we have also the electrophilic substitution reaction mechanism. These first two we did in the first video, and then we have now the nucleophilic substitution reaction mechanism, which we're going to do in this particular video. So we'll now start by how we define substitution reaction. We now have to understand the word nucleophile. Nucleophile. What's the nucleophile? So nucleophile is an electron-rich species which attacks a positively charged, or you can say electron deficient center. So nucleophile is electron-rich species. It's rich in electron which attacks a positive charge or deficient center, which is normally called electrophile. So nucleophile is rich in electron or has excess electron, and usually attacks a center that is deficient electron. The word nucleophile, nucleo means positive. Phile or philia means love. So it is rich in electron and attacks a positive center. So it loves to attack a center that is deficient in electron. That means the word nucleophile. So let's explain how nucleophiles are generated. Let us consider this compound, chloromethane, which contains which contains a methyl group and a chloro group. Now, you know that in chemistry, a single bond means two electrons are shared. That means a single bond. One electron from the methyl group, one from chlorine group. Then during fission process, what we call electrolytic fission, chlorine being more electronegative, we now move with the two electrons, put it away from this. So we now have methyl positive and chlorine negative. So this chloride ion is now called a nucleophile because it contains excess electron. That is why it's negatively charged. This electron it has. It pulls away the electron, it shares with this methyl group. While this one, the last electron, is called an electrophile or a carbocation. So you can see that. So how nucleophile generated? Nucleophiles are normally electron-rich species. Yeah, like for example, this. So there are many nucleophiles in chemistry. Examples of nucleophiles. Example of nucleophiles include negatively charged species, which include the fluoride ion, chloride ion, bromide ion, iodide ion. These are nucleophiles. Then we can also have the ethanoate ion. These are nucleophiles. So fluoride, chloride, bromide, iodide, ethanoate ion, or even generally the carboxylate ion. Also the hydroxide ion. These are nucleophiles. So they are negatively charged species because that negative charge indicates that they have excess electrons. So that's why they are called nucleophiles. Then do we have molecules that are neutral that are nucleophile? Yes, we can still have neutral molecules that are nucleophile. So neutral molecules that are nucleophile include water, ammonia, ethanol, and methanoic acid, etc. So let me leave this one, okay? Ethanol, methanol, and etc. These are nucleophiles, even though they have no negative charges, but they contain lone pairs on the central atom. Let's look at the structure of water and ammonia and explain why they are also nucleophiles, just like these ones. So let's look at water structure. In water, you have H2O, which consists of two hydrogen atoms linked to one oxygen atom. So if you do the bonding, oxygen is the central atom. The atomic number of oxygen is 8, which is 2, 6. 2 in the K shell, it's in the L shell. Hydrogen, the number is 1, which have 1 electron in the K shell. In the bonding of water, we now have this taking place. Oxygen being at the center, we have 6 electrons in the outermost shell. 1, 2, 3, 4, 5, 6. That is 6 valence electrons of oxygen. While each hydrogen atom will bring one electron to bond with oxygen. Hydrogen, asterisk to hydrogen. Hydrogen here bonded to oxygen. So the water structure now looks like the V shape of water structure. We have this due to the repulsion between the lone pair and the bond pair. We now have water structure in this nature. So why is water taken as a nucleophile? Because water has 2 lone pairs which it can donate for bonding. Nucleophile normally donate electron to the electrophile during chemical bonding. Electrophile is that one that has the positive charge or that one that lasts electron. So this is a nucleophile. So nucleophile are not only negative charge, they can also be neutral molecules provided they have lone pairs on the central atom, just like water. If I look at ammonia structure, why is ammonia a nucleophile? Look at ammonia NH3. Have 1 nitrogen atom bonded to 3 hydrogen atoms. The atomic number of nitrogen is 7. That is 2, 5. 2 in the K shell, 1 in the L shell. Why hydrogen is 1. Then this being the central atom, you show the valence electron, that is 5 alone only. Then the Lewis structure, the 5 electrons atmosphere. Why hydrogen? 1 from hydrogen there, 1 from hydrogen there, and 1 from hydrogen over there. That's the bonding now. So ammonia has a kind of a trigonal pyramidal shape. So that's the shape of ammonia. So our interest is not even on the shape. Our interest is that on nitrogen there's a lone pair on nitrogen which it can donate during chemical bonding. that means it's a nucleophile. So nucleophiles, we can say nucleophiles are generally Lewis bases. Nucleophiles are Lewis bases because Lewis bases are substances that donate lone pair of electrons during chemical bonding. So that's why we call them Lewis bases. So having done that, we'll now go over to what we have. Remember that our topic is a nucleophilic substitution reaction. We've been able to explain what is meant by nucleophile and then the nature of nucleophile, which could be negative ions or could be neutral molecules, provided they have lone pairs on the central atom, as we saw in water and also in ammonia. So now, we are now going to look at nucleophilic reactions normally occur, or nucleophilic substitution reactions occur mainly in compound called haloalkanes. Haloalkanes, or what called alkyl, and the old name alkyl halides. So we have this reaction occurring in such compounds, haloalkanes or alkyl halides. Before we go ahead, we have to understand the alkyl halide. What do you mean by alkyl halides? How to name the simple ones and how to classify alkyl halides before we go ahead to discuss the reactions in the nucleophilic substitution mechanism reactions. So the alkyl halides or haloalkane. So we now move to alkyl halides. The IUPAC name is haloalkanes. So, having done that, we should know that alkyl halides are compounds obtained when halogen atom or atoms substitute or replace hydrogen atom or atoms in an alkane. So that is alkyl halides. Compounds obtained when either a halogen atom or halogen atoms substitute or replace hydrogen atom or atoms in an alkane. We call them alkyl halides. For instance, this is an alkane. The simplest alkane is called methane. Methane. If I should remove one hydrogen atom from this methane, maybe this one, remove it, and replace it with a halogen, maybe call the halogen S, where S could be fluorine, bromine, chlorine, iodine. This compound now produces an alkyl halide, a very simple alkyl halide or haloalkane. Now, having done that, we can represent the monohaloalkanes. Monohaloalkanes or monoalkyl halides. So the monos of we can represent them with the formula RS, where R stands for the alkyl group. That R stands for the alkyl group. And that R or radical group, you have the formula CnH2n plus 1, where N starts from 1. So putting R in this we have CnH2n plus 1s. So you can see this and that. So this RS equivalent to CnH2n plus 1s. If I want to get the first member of the mono substituted haloalkanes, I replace N with 1. I'll have C1 H2 times 1 plus 1, then S. You see that? So this is going to give us C, that 1 carbon. 2 times 1 is 2 plus 1, 3, H3, and then S. If the halogen here is chlorine, CH3Cl, I'll call it chloromethane, taking the name of the halogen group, chloro. And then the name of the alkane, this is from the first alkane called methane. This is methyl, but the full name of the alkane is CH4. It derived from methane. So and I call it chloromethane. This is the IUPAC nomenclature. IUPAC name. Then if you want to take the common name, in the IUPAC name, you start from the halogen to name. In the common name, you start from the alkyl group. This is called methyl group. So this is now called methyl. Then the group will now end with chloride. This is the common name. So you can get it. See the difference between the two of them. So as a student in higher institution, you should know how to name both the name a compound, both the common name and the IUPAC nomenclature is of utmost importance. So having done that, perhaps if I use bromine here, bromine, if this were to be bromine, it would now be bromomethane or methyl bromide. Good. Then, if I take N as 2, I have C2, H2 times 2, replacing N with 2, then S. That gives you C2, H, 2 times 2 is 4 plus 1, 5, H5S. So this group C2H5 comes from an alkane called ethane. This is ethane. You remove one hydrogen from ethane, you have C2H5 called ethyl. See, just like the first one we did was methyl, CH3. How was it obtained? From an alkane called methane. Remove one hydrogen from methane, you have CH3 is now called methyl or methyl, as you pronounce the group. So you can see that. So if you look at this, how do we now, if we replace this, put a halogen there, let's say if I put bromine here, let me use bromine now. This is now by pack of a combination now called, we name from the halogen first, bromo group. Bromo, then ethane, because this is obtained from ethane. This is the IUPAC nomenclature. Then, if I want to name it the common name, I'll name this group first. Ethyl, then bromide, the common name. So you can see how to name mono-substituted haloalkanes. As simple as that. You see, it's very easy to generate the mono-substituted haloalkanes. If you know your alkane family, the alkane family, for example, the first alkane is called methane, CH4. If you don't know how to generate alkanes, you stream our videos. You have forgotten it, you stream our videos and see where we treated nomenclature of organic compounds. So there's a video where we did that for basic students. Basically those in grassroots or those in secondary school. So you should know that. Propane, butane. Remember that this is generated by adding CH2 to each member. So the homology series, 1 carbon plus this gives you 2. 2 plus 4 gives you 6. 1 plus 2 gives you 3. 2 plus 8 gives you 8. 1 plus 3 gives you 4. 2 plus 8 gives you 10. So what will be the next member? From the next member, I guess, right? You should know the formula. If you add this, you will have C5H12 called N10. So these are the alkanes. You see that? Then, if you want to get the alkyl group, the R group, instead of using this formula CnH2n plus, so where you substitute N with 1, so N with 2, so to give, you can see generate them from here. Remove one hydrogen each. One hydrogen remove, you have CH3. One hydrogen, you have C2H5. C3H7. C4H9. C5H11. Removing one hydrogen each from each of the alkanes. So look at the surface ANE. This one N with YL. Replace ANE for each of these names with YL. So instead of methane, call it methyl. Instead of ethane, remove ANE, call it this one ethyl. Instead of propane, you call this one propyl. Instead of butane, you call this one butyl. Instead of pentane, you call this one pentyl. You can continue to generate. This is hexane. H14, H13, hexyl. Hexane gives you hexyl. C7, continue adding the CH2. the CH2, please. Continue adding the CH2. You give you C7H16 heptane. What is it called? C7H15. This is called heptyl, and so on. You now generate the R group, the alkyl group R generated. So you see, another way of getting it without using the CnH2n+1 formula. We now have your alkyl group or your R group. This R, so each of them represent the R. So the alkyl group here is methyl, the alkyl group here is ethyl, propyl, butyl, and so on. So now, when you join the R with a halogen, because it's not a complete compound, that's why I gave a bond there, you now form a mono substituted alkyl halide. Like if I have CH3, maybe chlorine, and I have chloromethane, the IUPAC name, chloromethane, or methyl chloride, the common name. That is it. Or I can use the formula. If you want to do it this way, don't do it this way. Use the formula. Substitute. Since here carbon is 1, and I have C1H2 times 1 plus 1. Then bring in S, which could be chlorine. That becomes C, 1 carbon, 3 hydrogen, the same formula. So either by substitution or by derivation from Alkenes, you get it. So you see have the same formula. So if I use the score member, perhaps C2H5, I put bromine. This is called bromoethane or methyl bromide by IUPAC, by common name and IUPAC convention and common name. Or I go by the formula RS. In this one now, this is the general formula. In this one now, carbon is 2, and I have C2H2 times 2 plus 1. Then bromine comes in. This becomes C2H5Br, called bromoethane, or the common name ethyl bromide. So that is it. We have introduced the mono substituted haloalkanes. Okay, our business today is not on nomenclature, but you can still go through our video and see where we did nomenclature of organic compounds and still key into what we are doing. So having done that, we're now going into classification of alkyl halides. So how to classify the mono substituted alkyl halides. So the first is the simple. The first one we can call it the simple alkyl or simplest alkyl halide. The simple alkyl halide is nothing but methyl halide. Methyl halide obtained from methane. This is methane structure. Methane structure. Remove one hydrogen there and bring in a halogen, which could be S, any halogen of your own choice. So when you have this is the simplest type of halide, a monosubstituted alkyl halide called methyl halide. If I have chlorine here, I'll call it chloromethane. If I have methyl chloride, as I taught you, if I have bromine here, I'll call it bromoethane or methyl bromide. If I have iodine here, I'll call it iodomethane or common name methyl iodide. So the simplest classification of monosubstituted alkyl halide is the methyl halide. The methyl halide. So how that the first one. Now go to number 2 classification. Number 2 is called primary or 1 degree alkyl halides. So when we have or haloalkanes, this can also be called haloalkanes, please. So when we have 1 degree, assuming we'll go to methane, this is methane, or we'll go to the primary alkyl, that is the simplest alkyl halide. So that is it. The simplest alkyl halide, please, which could be methyl halide. Yeah, that's what it means. And replace one of the hydrogen here. There are 3 hydrogen atoms you see here. It was the halogen. Replace one of the hydrogen atoms with an alkyl group. So we now have this. R, C, H, H, S. This is a primary or 1 degree alkyl halide. Look at it very well. You see that in 1 degree alkyl halide, you have 1 alkyl group bonded to the carbon that that is linked to the halogen. One alkyl group bonded to the carbon that is linked to the halogen. The other atoms are hydrogen, hydrogen. This is called a primary alkyl halide or halocane. So that is it. Then we'll take example of primary haloalkanes. So let's take example. An example is this. This is a primary haloalkane. So let's find out why it's called primary haloalkane. Open the structure. The first carbon, you write it out. Bond to hydrogen, you show the bond, the single bond to hydrogen atom. That is H, H, H. Go to the second carbon with a single bond. There are two hydrogen atoms, one here, one there, and then go to chlorine, a single bond to chlorine. So you see, you have this. This is called, if I should name it, when you want to name alkyl halides, number the carbon atom. If I the longer chain, there are two carbon atoms on the straight chain or longer chain. And then number the carbon atoms from the carbon that is bonded to the halogen. This is the one, keep that one number one, preference, 1, and then 2. So this is now called 1-chloro. The carbon is 2 carbon, and the alkane that has 2 carbon is called ethane. 1-chloroethane. So that is the IUPAC name. We want to take the common name. The common name is called, remember the common name, the alkyl group goes first. The alkyl group is this. There are 2 carbon here. Remember that this compound is written as writing C2H5Cl. 2 carbon, 5 hydrogen, 3 plus 2, and then 1. So the common name is ethyl. This group is called ethyl chloride. So common name, IUPAC name. So you can see the compound very well. So this is a primary alkyl halide. Why is it primary? It may look confusing here. To check whether it's primary very well, look at the structure again. Look at the structure, you see that, let's cut it here. You leave the carbon that is carrying the halogen, because is this one, the number 1 carbon. Leave it alone, don't compress it. Then the other carbon, you have carbon here, carrying, compress this one, compress this group, that gives you CH3. Then link it to the other one, you have CH, chlorine. So you can see one alkyl group to the carbon, bonded to the carbon of the halogen. The other ones are hydrogen atoms. So one alkyl methyl group bonded to the carbon of the halogen is, that makes it primary. And that's why the name goes with 1 degree, 1-chloroethane. That was the reason for the 1 you have there, or 1 degree you have there. So this is a primary alkyl halide or primary haloalkane. Another example is this. CH3, CH2, CH2, CH2Br. This is also a primary alkyl halide. So why do we say it's primary alkyl halide? Look at the structure very well. If I open the chain, the first carbon goes with 3 hydrogen. Second goes with 2 hydrogen. Third goes with 2 hydrogen. Fourth goes with 2 hydrogen. And you can see bromine here. So why is this called, they get the name first. So name it, the longest carbon chain is 4. 1, 2, 3, 4. There's no branches, only straight chain. 1, 2, 3, 4. And in non-brain, you number the carbon that is close to the halogen, that is number 1. So 2, 3, 4. So there are 4 carbon. And alkane that has 4 carbon is called butane. So this is now called 1-bromo, because the bromine is number 1. 1-bromo butane. The words are joined together. Then this is the IUPAC name. The common name is called butyl bromide. Because it's something as saying, count the whole carbon, 1, 2, 3, 4. C4. Add the whole hydrogen, 5. 3 plus 2, 5, plus 2, 7, plus 2, 9. H9. So this is butyl group from butane. Butyl, then bromide, the common name. So now let's explain why it is classified as 1 degree. For the fact that we're seeing 1 here means 1 degree. So, or primary alkyl halide. So let's explain further with this structure. As I said in the other example, the carbon that is linked to the halogen, leave it with the group around it alone. Don't compress. Another carbon compressed. They are 1, 2, 3. You join them together, is C3H7. 1, 2, 3. Then the hydrogen is 1, 2, 3, 4, 5, 6, 7. That is this group. Then join this. We have CHHBr. So this is primary because you have only one alkyl group, propyl group, bonded to the carbon of the halogen. The other ones are not, the other ones are hydrogen. That one is a primary alkyl halide. So this is the second way of clarifying alkyl halides. After the simplest kind, they will have primary. Then the third kind of clarifying mono substituted haloalkanes is what we call secondary. So remember we are clarifying mono substituted, or let me call it monoalkyl halides. Simple as that. Secondary or 2-degree alkyl halides. So when we have 2-degree alkyl halides, let's go back to the simplest alkyl halide, the methyl halide. The structure, that's the methyl halide. So you remove one of the hydrogen atom and also remove another one. Bring in an alkyl group to replace this. Bring in another alkyl group to replace this. We now have CH, H, R, okay, R here, and the halogen there. This is now called a secondary or 2-degree. Normally prevalent with sec, 2-degree alkyl halide. So in 2-degree alkyl halide, you have two alkyl groups bonded directly to the carbon of the halogen. Two alkyl groups bonded directly or linked to the carbon carrying the halogen. If it's primary, you only have one alkyl group. The here would have been hydrogen, but because it's secondary, you have two alkyl groups. So that's why it's called secondary or 2-degree alkyl halide. Example of 2-degree alkyl is the compound called 2-chlorobutane. 2-chlorobutane. So let's look at the structure. So this compound is called 2-chlorobutane and is an example of secondary alkyl halide. So let's verify why it is so. Apart from the 2 is having, that 2 very confirm that is secondary 2 degrees. So let's verify why it is 2-degree alkyl halide. So what do we do? Look at this. As I said, the carbon, the carbon carrying halogen is on this, is on the second position. So it's bonded directly by hydrogen and chlorine. So we'll circle it. We'll not compress it. Any other group you see by the side, you compress this one. This is CH3. You compress this one. This is C2H5. So you now have C2H5. That is on the left hand side, linked to carbon, hydrogen, chlorine, and then CH3. So this is the CH3 at the extreme. On the right hand side is C2H5. Then this is the one carrying the halogen uncompressed. So you're seeing 2 alkyl groups, a T group. This is methyl group 2 linked to the carbon carrying the halogen. So you see that why it is called secondary or 2-degree alkyl halide. So we'll take another example. The another example I'm going to take is a one called 2-chloropropane. So before we go to another example, the IUPAC name of this compound is 2-chlorobutane, yes. Then the common name is called secondary butyl chloride. So why do we call secondary? Because this is on 2-degree, number 2. So butyl, and the whole carbon, this is 2, 3, 4. 2 plus 1, 3 plus 1, 4. That is butyl. Then 5, 8, 9. That is C4H9Cl. It should have been called butyl chloride, but the secondary comes in because the chlorine is, look at the structure, the chlorine is bonded to the carbon carrying 2 alkyl group. So now call it secondary butyl chloride. So having done that, we'll take another example of secondary alkyl halide. And the example is this compound called 2-chloropropane. Propane has 3 carbon atoms. So I put chlorine at the middle, or let me use bromine, 2-bromopropane. So you see that. So that is also secondary alkyl halide, because these are number 2, 1, 2, or 1 to anywhere you start from. This carbon will be number 2, carrying the halogen. So this is called 2-bromopropane. It's secondary. So look at the structure very well. Let's leave this one kind of halogen alone, and then compress this and that. That will give us CH3, CHBr, and then under CH3. So 2 alkyl groups linked to the carbon carrying the halogen. That means it's secondary alkyl halide. So 2-bromopropane, or we can call it, the common name is called isopropyl bromide. Isopropyl bromide. So this is also a secondary alkyl halide, or 2-degree alkyl halide. Okay, so what if we have this compound? Because understanding this calculation will help us to understand SN1 and SN2 mechanism. That's why we're doing it first, as a kind of a initial aspect of the topic. So having done this, so how would we call this? What would we call this compound? We have an iodine, iodide ion here. So this is a halogen. So name it. This will be from number 1 to, the number here 1, 2. The carbon here closest to halogen is number 2. Start from this end, 1, 2, 3, 4. Prefer a lower numbering. So 1, 2, 3, 4 to this carbon. 1, 2, 2 is preferred to 4. We use a lower number. So this is now called 2-iodo. There are 1, 2, there are 5 carbon atoms, 2-iodopentane. That is it, the compound. So it's secondary because of the 2 degree on it, secondary alkyl halide. Then if you want to give the common name, if you count the whole carbon, 1, 2, 3, 4, 5, C5. The hydrogen, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, H11, and then iodine. This is an alkyl group. So this is pentyl. So pentyl iodide. That's how the common name will go like iodide. But to show that the iodine is bonded to the secondary carbon, we now call it secondary or sec pentyl iodide. Sec pentyl iodide. So to prove your structure, you can, this is the one carrying the halogen, leave it alone. Compress this group here. So this is C3H7. You can count it very well, C3H7. So I will delete it. And then write here C3H7, an alkyl group, an R group. On this side, I have CH3. So you now have 2 alkyl groups bonded to the carbon carrying the halogen. That means the secondary alkyl halide. So having done that, is very easy for you to name. So you can easily name secondary alkyl halides. You want to use the common name, very easy. Common name, just like you have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. You have chlorine here. So this, the IUPAC name is very easy. The IUPAC name of this compound, to name that, give the IUPAC nomenclature, you just number it. The carbon chain from the end that give the smallest number to the halogen. 1, 2, 3, 4, 5. This is long. 1, 2. This is preferable. Common name is now 2-chloro, and then since it's 6, he's join all the words together. Separate the words from the number with hyphen. So this is the IUPAC nomenclature. But if you want to take the common name, what you have to do is identify the kind of halide it is secondary. Then count the whole carbon, that is 6. Count the whole hydrogen, 1, 2, 3, 4, 5, 6. Plus 6, okay, plus 5, 11, 12, 13 hydrogen. and then one chlorine. To name it now, this is from hexane. I call it hexyl chloride. But I now attach secondary in front to show that it's the secondary or 2-degree alkyl halide. So having done that, we will now go to the fourth classification of alkyl halide. The fourth is called tertiary alkyl halide. Tertiary or 3rd-degree alkyl halides. So what do you understand by tertiary? Tertiary alkyl halide. Then go back again to the simplest alkyl, monoalkyl halide like the methyl halide. Then replace this with an alkyl group. The whole hydrogen, replace all of them with alkyl groups. So that is it. It gives you tertiary. So for example, I have the full structure R. That means in tertiary alkyl halide, there is no hydrogen bonded directly to the carbon. They're all alkyl groups, 3 of them, and then 1 halogen. We now call that tertiary or 3rd-degree alkyl halide. Tertiary or 3rd-degree alkyl halide. So let's take an example of a tertiary alkyl halide and see the way it looks like. Let's replace the alkyl group with methyl group, CH3. They use similar group. You can see different alkyl groups anyway. CH3, and then this place with chlorine. So this is a tertiary alkyl halide. It's a tertiary alkyl halide or 3rd-degree alkyl halide. So you can see that. So around the carbon of the halogen, we only have alkyl groups. So we can draw the full structure. I have 1, 2, 3. There are 4 carbon. 1, 2, 3, 4. 4 carbon. We then put the hydrogen atoms. So this alkyl group is here. Halogen is there. So you should know how I drew the structures. The structure, please. If you look at it, the longest chain here is 1, 2, 3. Or you can see this way, 1, 2, 3, or 1, 2, 3. So you can count it as a branch chain or as a straight chain. Just find the longest chain. So if I have 1, 2, 3, these are the straight longest chain. I don't have to count the whole carbon. Straight way traffic. 1, 2, 3. Or I can say 1, 2, 3. It's still number 3, 3 carbon. Or I can say 1, 2, 3. So anywhere how you want to use it, it's still giving you 3. So since 3 is the longest chain, I'm taking 3 now. So the longest chain is 3 carbon. And this chlorine and methyl are number 2 carbon. So if I have here number 1, number 2, number 3, so this is the structure. So this compound is now called, there are 2 substituents on this carbon, chloro and methyl group. So in naming by paper convention, we first of all name by Abeka order. Chlorine come before methyl, and I call it 2-chloro, 2-methyl. The longest chain now is any error? Let's see, 1, 2, 3. Error somewhere. This is 1, 2, 3. So the correct structure is 1, 2. I have to wipe off this. It's 3 carbon. So 1 on the straight chain. 1, 2, 3. So 1, 2, 3. So 2-chloro, 2-methyl, then 3 carbon is propane. So that is the IUPAC nomenclature or conversion of this compound. 2-chloro, 2-methyl, propane. You see that? So having done that, what else do we do? So why the common name? The common name is, to get a common name, you can't the whole carbon. Remember that if you compress this, you have CH3. If you compress that, you have CH3 again. You have CH3, a methyl group, alkyl group, CH3, and also another CH3. So 3 alkyl groups. 1, 2, 3. As you have 3 alkyl groups, so look at it. CH3, CH3. 3 alkyl groups. Bonded the carbon carrying halogens. This compound, this structure are the same thing, just rearrangement. If you turn it 180 degrees or thereabout, you get this structure. So they're the same thing. So this 3 alkyl groups bond the carbon of the halogen. That means it's tertiary or 3rd-degree alkyl halide. So we have to open the chain to name it properly. But we want to take the common name. I don't have to open the chair. What I have to do is count the whole carbon. 1, 2, 3, 4. I have C4, hydrogen, 3, 3, 6, plus this one, 9, H9, Cl. This is supposed to be called chlorobutane, based on the common name. Chlorobutane, that's the common name. But, sorry, not chloro, but these are back names, sorry. Common name is butyl chloride. But in common name, you name the alkyl group butyl chloride. Yeah, please. Don't join them together. Butyl chloride. But it's not enough to do that, because if you call it butyl chloride, nobody will know whether it's primary, secondary, or tertiary. Now, since it's tertiary from structure, it's 3rd degree. Tertiary, we now write in front that hyphen. That means tertiary or 3rd degree. That butyl chloride. That's the actual common name. That butyl chloride. That butyl chloride. So having done that, we are seeing how we can classify alkyl halides from simple alkyl halides, primary, secondary, and then tertiary alkyl halides. Now let's discuss hybridization. In alkyl halides. So, I know that a carbon atom in haloalkanes or alkyl halides is sp3 hybridized. The carbon atom in haloalkanes has sp3 hybridization, or we say it's sp3 hybridized. How do we prove that? To prove that, we have to choose a simple alkyl halide. For example, let's choose chloromethane. Now, let's look at carbon. Carbon has an atomic number of 6. The EC is 1s2, 2s2, 2p2. That is EC of carbon. If you draw the beta diagram, have 1s with 2 electrons, 2s with 2 electrons, 2p also with 2 electrons, and 2p is the subenergy level. We have ps, py, pz inside 2p. Now, going by Horn's rule, electrons will not be given to only one orbital. It will go singly to the end before it starts doubling. So there are 2 here. I'll give 1 here to this and 1 to this one. One is empty since I only have 2. So this is what's called the ground state electronic configuration of carbon. Then carbon does not undergo hybridization in ground state. It undergoes hybridization in excited state. And in the excited state of carbon, 1 electron from 2s is promoted to fill the 2p's after absorbing photons of light energy. So now 1 electron from 2s will be promoted to enter 2p, so that each of the p orbitals will have 1 electron each, or will have a single electron. So we'll have this. So 1 electron here will jump after absorbing the right energy and move to fill up the 2pz. So you look at the carbon now, you see that carbon has 3 orbitals that contain single electrons. 1 of the 2s, 1 of the s, that is 2s, and 3 of the p's. So that will say that carbon is sp3 hybridized in alkyl halides. So now, to round up the hybridization, you can see this, there are 3 hydrogen atoms here in methyl chloride. So 1 hydrogen atom brings electron. This is from hydrogen. And that hydrogen atom here, dotted line, and that hydrogen here, atom here. So from hydrogen, since there are 3 hydrogen atoms, hydrogen again, 1, 2, 3. Then chlorine will now bring 1 again to fill up this place, since there's 1 chlorine atom. So in all, we have sp3 hybridization scheme in alkyl halides, using methyl chloride as a simple example. So having done that, we now move to our main topic. This is just for you to understand the process involved and have a good knowledge before we go to nucleophilic substitution reaction. We now go to nucleophilic substitution reaction mechanism. We are defining what is meant by a substitution reaction as a reaction that involves replacement of an atom or group of atoms by another atom or group in a saturated organic compound. And we are defining what is meant by a nucleophile, which is an electron-rich species that loves to attack an electron-deficient center, the nucleophile. So, example of nucleophilic solution is the reaction between bromomethane or methyl bromide and sodium hydroxide. In this reaction, the hydroxide ion with the nucleophile, remember, when sodium hydroxide dissociates, it produces sodium, which is positive, and hydroxide, which is negative. Negative ion here means that it is electron rich. Goes replace bromine under electron rich substance. So to give you CH3OH, methanol, and sodium bromide. So this is example of nucleophilic substitution because this is a nucleophile going to substitute bromine or a weaker nucleophile coming in to replace it. We now have a nucleophilic substitution reaction taking place. Now we're going to types of nucleophilic reaction mechanism. So there are two types of nucleophilic substitution reaction mechanism. The first type is called SN2 reaction mechanism. One is called SN1 nucleophilic substitution mechanism. So SN2 stands for substitution. Nucleophilic. Bimolecular. That too, bimolecular reaction mechanism. While the one is called substitution or stand for substitution nucleophilic. Unimolecular. That one is uni. Reaction mechanism. So these are the two reaction mechanisms we have in nucleophilic substitution reaction. Without wasting time, I'm going to start with the first one, SN2 reaction. So we're going to list the key features of this reaction. The features include, or the first is the definition. We say it's a nucleophilic reaction. The nucleophilic substitution reaction let me put it this way, is a single step or concerted nucleophilic substitution reaction in which the bond making between the nucleophile and the carbon center or carbon atom and the bond cleavage between the nucleophile, the carbon atom and the leaving group occur the same time or simultaneously. So we have, say, it's a single step that it occurs in one step. Single or concerted step nucleophilic substitution reaction in which the bond making process between the nucleophile and the carbon atom and the bond cleavage process between the carbon atom and the leaving group occur the same time. I repeat, I say it's a single step or concerted step nucleophilic substitution reaction in which the bond making process between the nucleophile and the carbon atom and the bond cleavage or process between the carbon atom and the leaving group occur at the same time. What it means is that both the bond making between the nucleophile that is coming in and the leaving group that's going out, the bond breakage occur at the same time. So that is it. Number 2 point we should know that is it involves what we call a backside attack of the nucleophile. So that in this reaction, nucleophile attack the carbon from the back or from the rear. So it involves a backside attack of the nucleophile on the carbon atom. Okay. Number 3 point is that it leads to the formation of a transition state. So in this reaction, an unstable transition state is formed. So it leads to the formation of a transition state. So you can see what we have there. Number 1 is a single step or concerted, CONCERTED, nucleophilic substitution reaction in which the bond making process between the nucleophile and the carbon atom and the bond cleavage process between the carbon atom and the leaving group occur at the same time. Number 2, it involves a backside attack of the nucleophile on the carbon atom. Number 3, it leads to the formation of a transition or unstable transition state. Then, with the other key factors involved here, number 4 about SN2 mechanism is that it's a biomolecular reaction we said before. It is a biomolecular, that was the reason for that too. Biomolecular reactions are reactions that involve 2 molecules in the elementary step. The biomolecular reaction in which the rate of reaction of the rate determining step depends on the concentration or concentrations of the substrate and the nucleophile. You know, from your knowledge of physical chemistry, the rate determining step is that step that determines the rate of reaction. That's the slowest step of the reaction. So the rate equation for SN to begin by R equals where R is the rate of reaction, K is the specific rate constant, multiplied by the concentration of the substrate, that the substance that has been attacked, the reactant, and then that of the nucleophile. So this reaction is bimolecular because the rate of reaction brings in 2 substances, the reactant and the attacking reagent, which you call the substrate, and the nucleophile attacking it. So the power to which the substrate is raised is 1 here. Nucleophile raised to power 1. So 1 plus 1 gives you 2. That's why it's called a biomolecular reaction. What's kind of that reaction? One first order to each of them. So you have that. Then number 5, it occurs mainly in methyl halides and primary or 1-degree haloalkanes. We'll explain what is meant by primary haloalkanes and then the simplest haloalkane called methyl halides. So SN2 reaction is witnessed mainly in primary alkyl halides and also methyl halides. So it can also occur, this one it may, not a must, It may also occur in secondary or 2-degree alkyl halides, depending, and that depends on the nature of the solvent or the type of solvent used in the reaction and the nature of the nucleophile. So, but as a rule, it occurs mainly in methyl halides and in primary alkyl halides. For it to occur in secondary alkyl halide depends on the kind of solvent used and the nature of the nucleophile. It does not occur in 3-degree alkyl halides. I repeat, SN2 reaction does not occur with 3-degree or tertiary alkyl halides. So, having done that, then we'll have other things. We can say it. Another factor, number 6, about this reaction is it leads to what called Walden inversion. Walden inversion. So it leads to Walden inversion. So let's explain what is meant by Walden inversion. With an example here. So look at this structure here, where the iodide ion is attacking a compound. So have the AT group there, and then we have the 3-dimensional structure, hydrogen, then the wedge carrying the methyl group, and then we have an anion there, chloride ion attached here. So in this is an example of nucleophilic reaction between this compound called 2-chlorobutane and iodide ion. So if this is the nucleophile coming in to attack or to have what's called a backside attack, attacks the carbon from the back, not from the front, because chlorine is also negatively charged. So if chlorine iodine cannot come from the same side from chlorine because like charges repel. So you come from the opposite charge to minimize repulsion. So after attacking it, chlorine will now leave, and while iodine will fix itself to carbon. We'll now have a product. From the product, iodine comes in from the back. We have iodide ion, sorry. Then we now have the CH2, CH3, and then have again the hydrogen atom, and then the wedge carrying the methyl group. So you see this, and then the halogen has left. So plus Cl going out. The chlorine had left. So you see the product, the iodine has replaced chlorine in this reaction. But look at the reactant and look at the product. You see there's an inversion of configuration here, whereby look at this group, the AT group, hydrogen, and then the methyl group are on the right hand side of the carbon of the plane. But on the left hand side, sorry, if you go to the product, they now appear to be on the right hand side instead of being on this side. I repeat myself, the AT group, ethyl, C2H5, hydrogen, and the methyl group appear to be on the left hand side of the plane of the carbon. Then in the product, they now shift to the right hand side. This is what's known as Walden inversion. So nucleophilic reaction leads to inversion of the final configuration of the final product, which is known as Walden, named after the discoverer, Walden inversion. So having done that, then the next, number 7 point we should know about nucleophilic reaction is that the kind of solvents that are used in nucleophilic reaction is very important. So the normally occurs in the presence of, number 7, SN2 reactions occurs in the presence of what we call aprotic solvents, aprotic polar solvents. So, what kind of solvents are said to be aprotic? Aprotic solvents are those solvents that do not have hydroxyl group. They don't have hydroxyl group, OH group, and they cannot form hydrogen bond with the substrate. We call them aprotic solvents. So, example include dimethyl sulfur oxide, dimethyl sulfur oxide, CH3, dimethyl sulfur oxide. Look at the structure. Two methyl group, that di, methyl, then sulfur oxide. So it's an aprotic solvent. And that solvent is acetone. It's also an aprotic solvent, acetone. Acetone is what is known as propanone now. Then another example is dichloromethane, CH2Cl2, dichloromethane, and then diethyl ether, C2H5O. So this is in order of decreasing polarity from the most polar to the most polar to the least polar. So SN2 reactions occur in the presence of these solvents. So any reaction that involves alkyl halides where these solvents are used will normally take place by SN2 reaction mechanism. So having introduced SN2 reaction mechanism, we're now going to take an example, at least two examples, to illustrate SN2 reaction mechanism. So we now have the first one is alkaline hydrolysis of methyl bromide. So we're looking at SN2 reactions, the mechanism, how it goes. Alkaline hydrolysis of methyl bromide. So the equation can go like this. This is methyl bromide. Alkali means presence of sodium hydroxide, where the nucleophile replaces the bromine ion. Now CH3OH plus sodium bromide. So why would this reaction occur by SN2 mechanism? Look at the alkyl halide given to you. This is a simple alkyl halide. It's a methyl halide. As I said, methyl halide and primary alkyl halide undergo SN2 reaction mechanism. You see, that's the reason why this reaction must occur by SN2 reaction mechanism. So now let's look at the steps involved in this reaction, in the mechanism. So the first step, or step 1, the mechanism is this compound. Of course, before we go on, this compound with the alkyl will ionize to bring the nucleophile out, sodium ion and hydrogen ion, which is the nucleophile, is produced. So the hydroxide ion is the nucleophile we have in that reaction. Hydroxide ion is the nucleophile we have in the reaction there. So let's look at how the reaction takes place. So the first step in that mechanism is the nucleophile is going to attack the center from the opposite side of the leaving group. So nucleophile attacks the carbon center from the opposite side of the leaving group. So let's draw the structure. The three-dimensional structure of this compound have a carbon at the middle, you have hydrogen, have another hydrogen with a broken line to show its position on the plane, have a wedge carrying the third hydrogen. They have bromine. The bromine is the group that will leave, called the leaving group. The nucleophile coming in now is hydroxide from sodium hydroxide. So we now have the nucleophile coming from the back. So let oxygen hydrogen to attack the carbon. So look at the arrow going down there. So the nucleophile comes to attack the carbon. The bromine also tends to what? To start departing, because I told you in this SN2 mechanism, bond making and the bond breaking occur the same time, simultaneously. So the next thing is going to have you don't have to say step 1 because it occurs in a single step. So we don't have step 2. So it's a single step, or as I say, it's a concerted reaction. So in the next differential state is formed. Transition state have carbon, hydrogen, the hydrogen at the bottom, the one with a wedge here, and then broken line, and also under broken line, OH attaches itself. So we're going to give this bromine partially negative, hydroxyl also partially negative, carbon center partially positive. So this is called the transition state of the reaction. So what do the broken lines signify? The broken line here, it signifies that the bromine is leaving, the bond is broken partially, the leaving group. What the broken line here shows that the hydroxy group has partially attached itself to the carbon center. So nucleophilic reaction is driven by the attraction between the carbon, which is positive charge, and the nucleophile negative charge that is coming in. So finally, we have the final product. In the final product, the bromine will now finally depart, and then the configuration of this reactor will change. So that is Warden inversion. We now have the final product as this. We have a H, the wedge, and then bromine attaches itself. Hydroxide attaches itself to give you methanol, that's the compound there, and then the bromine ion leaves. So you can compare this configuration and this configuration, the group here, all the group atoms here, and on the left hand side, and now on the right hand side of the final product. And that is what is meant by Warden inversion of configuration. So that is it. So that is a example of a nucleophilic SN2 nucleophilic substitution reaction. Its mechanism, a very simple thing. So repeat the process. The nucleophile generated by the reagent ionizing give you the native ion. Then you draw the three-dimensional structure of this compound. Carbon at the center, link the three hydrogen atoms, one with a thick line, one with a wedge, and one with a broken line. Then bromine, the leaving group, on the right hand side. Then the nucleophile will attack on the left hand side from the back of the carbon, because the nucleophile has similarity charge as the bromine, so it cannot attack from this side because they will repair themselves. So we call it the backside attack. So coming in, it's going to attack itself here. So this is the transition state whereby the nucleophile has attached itself with the broken line, broken bond, and the bromine is also broken, because the broken line on the right hand side for bromine shows the bromine is living. It's a living group, it's a good living group. But the broken line on the left hand side so that the hydroxide is attaching itself, or has attached itself partially to form a new bond. So finally, the bromine will now leave the part. Finally, you will now have your final product. But there's going to be an inversion of configuration that the atoms on this plane will now appear on the other plane. Warden inversion. So having done that, we'll take another example of a SN2 reaction mechanism. Number 2 example is what we call alkaline hydrolysis of ethyl chloride. Formula is C2H5-ethyl, then chlorine plus sodium hydroxide. The hydroxy group replaces the chloro group. We have ethanol produced, and then sodium bromide, sodium chloride please produce. So why would this reaction occur by SN2 substitution mechanism? So why will it occur in that way? Let's see. If you look at this, look at the structure of this compound. C2H5 and chlorine. So you have to find out whether is a secondary, primary, or tertiary alkyl halide. So as I've explained to you today in this video, so let's now compress this. This is the carbon dioxide halide. So this group is just CH3 linked to this. So an alkyl halide that you have only one alkyl group attached or bonded to the carbon of the halogen is the primary. These ones are not alkyl group. It's the primary alkyl halide. And as I told you, primary alkyl halide and also methyl halides undergo SN2 mechanism. So since this is primary alkyl halide, the reaction will be by SN2 reaction mechanism. Because in various exams in the high institution, your lecturer or your teacher will not tell you the method to use to do this. They will tell you illustrate substitution nucleophilic reaction. You'll be the one that will find out whether the reaction will follow SN2 or follow SN1 reaction mechanism. So what I'm going to do now is, this is the structure of the compound, CH. I'll just write the condensed formula. And then this is it. I'm going to draw the structure. The central carbon is this, the one carrying the halogen. Halogen appears on the right hand side. Then there is methyl group here. So I'll draw methyl group on top there. Then there are also two hydrogen. I use a wedge, broken line for one of the hydrogen atoms, and a wedge for the other hydrogen atom. So you see how to draw the three-dimensional structure. So this is sentiment at this compound. One carbon, the carbon at the center, the one carrying halogen, the one you put at the center. Then the two hydrogen, the methyl group, and then the halogen group. Then the nucleophile will come from this compound, ionizing this compound. This is a reagent, sodium ion and hydroxide ion. So the hydroxide ion will now attack oxygen first. Then will now attack the nucleophile, the substrate from the back because of the repulsion between the negative charges, the hydrogen and chlorine. So this cannot attack from this side. So we have that. So when this happens now, we're going to form the transition state. The transition state, we have carbon at the middle, then we have CH3 up there, then down we have hydrogen, then the wedge carrying another hydrogen, then have a bond. This bond is broken partially, while this bond is formed partially. So this is the transition state. You can see that. So this is partial negative, partial negative, partial positive. So this is the living group. It's living. So I have to show that I show that it's going out. So having done that, we now have a final product. So our final product will be in this nature. This group departs now. We now have inversion of configuration, that widening inversion, whereby all the groups, all the groups on this side here will appear on the other side. We now have CH3, have a hydrogen, the wedge linking to carbon, and then the hydroxyl coming from the back. So, and then chlorine ion will now go away as departing anion or nucleophile. So you can see that very well. You see that this configuration is opposite to this configuration. And if you look at this compound and this compound is the same, ethanol, 2 carbon, 1, 2, that is 2 carbon, 3, 4, 5 hydrogen, OH there, ethanol produced. So you can see that very well, that we have formed a product. So let me draw it very well for it to be very clear to you. I have a carbon, CH3, then we have hydrogen here, the wedge for another hydrogen, and then on this side have OH attaching itself. This is the final product of the reaction. So that is it. So with that, you understand the same thing. This is the mechanism of SN2 substitution nucleophilic reaction, bimolecular reaction mechanism. The next we're going to go to is, let's look at the energy profile diagram of an SN2 reaction. You want to draw the energy profile of SN2 reaction, you just put this down. From your O level, you learned how to draw energy profile diagram. So this place you call it energy in joules. This place you call it reaction pathway or reaction coordinate without any unit. So you draw a vertical axis, you also draw a horizontal axis. The vertical shows energy in joules, horizontal shows reaction pathway, or you can still call it potential energy. Then you draw your curve. Let's assume that we'll have an exothermic reaction. So the product should be lower. The product level should be lower than the reactant level. Look at the reactant, look at the product, going lower than the reactant. So what you write here is your reactant. For example, this reaction we use today, which involve ethyl chloride and sodium hydroxide. Put them on the reactant level, that is here. So this is your reactant. The product formed is nothing but we produce ethanol, you know, right? Ethanol C2H5OH, and maybe chloride ion produces that. This is the product. So you can see the product is lower than the reactant level. Look at it. The level, reactant, and then product. So we'll now draw on top of the hill. We're going to draw the transition state. This transition state is now drawn on top of the hill, TS. So you draw this structure on top of the hill, that the particular structure. So you draw it. Then from this point, you draw a straight line to the level of the line of the reactant. This line is called activation energy. The activation energy. You also draw on that line to the reactant level to the product level. Let's just extend it a little. You draw on that line. That line is called enthalpy change or heat of reaction, which is negative joules, because it's exothermic. The product level is less than the reactant level. So we have that exothermic reaction. So that is an example of how to sketch a diagram for energy profile diagram for SN2 reaction mechanism. So having done justice to SN2 reaction mechanism, we'll now move to SN1 reaction mechanism. So SN1 reaction mechanism. So by definition, SN1 means substitution reaction. Substitution nucleophilic unimolecular reaction. Substitution nucleophilic unimolecular reaction. So what is it all about? The type of reaction in the living group. It is the type of reaction of nucleophilic substitution reaction in which the living group completely detaches itself before the nucleophile attacks the carbon atom. So in this reaction, the living group is unlike SN1. In SN1 reaction, both the bond making and the bond cleavage occur at the same time. But in this one, the living group completes that itself before the nucleophile comes in to attack the carbon. So number 2 is it leads to the formation of a carbocation in the rate determining step or slope step of the reaction. So it gives rise to a carbocation, unlike the SN1 reaction, SN2 reaction mechanism. The number 3 is that it is unimolecular. So reaction is unimolecular. Otherwise, that one means unimolecular. Is unimolecular. And the rate of reaction of the rate determining step depends only on the concentration and the rate of reaction depends only on the concentration of the substrate. So I repeat, reaction is unimolecular, and the rate of reaction depends only on the concentration of the substrate. So the rate equation given by rate equal to the rate constant multiplied by the concentration of the substrate. So the rate of reaction doesn't depend on that of the nucleophile, on the concentration of the nucleophile. That's why the nucleophile doesn't appear in the rate equation, unlike SN2 mechanism. So that's why in molecular, it involves only one substance, a substrate. Nucleophile is not involved in the rate determining step. So number 4. Number 4 feature of SN1 reaction is that it occurs mainly in tertiary or third-degree alkyl halides. So it occurs in third-degree alkyl halides because third-degree carbocations are stabilized. So it doesn't occur in 1 degree. But it can still occur in 2 degrees, just like SN1, SN2. So it can occur in 2 degree or secondary alkyl halides, depending on the nature of the solvent and also nucleophile. So, but basically, it's mainly found in third-degree alkyl halides, while SN2 occur in in methyl halides and primary alkyl halide, but SN2 occurs in methyl halides or primary alkyl halide, but SN1 occurs in tertiary alkyl halides. Both SN1 and SN2 can occur in secondary alkyl halide, but that depends on the nature of the solvent being used and the type of nucleophile or the structure of the nucleophile that is consigned. So, having done that, then the kind of solvents. So number 5, we say that SN2 reactions occur in aprotic solvents, aprotic polar solvent, but SN1 reaction occurs in protic solvents. So what are protic solvents? Protic solvents, unlike aprotic, are those solvents that contain the hydroxy group, OH group, and they can form or donate hydrogen bond to the substrate. We call these ones protic solvents. So what are the examples of protic solvents? They include water, being the most polar of all of them, followed by low molecular weight organic acid and the alkanols. For example, methanoic acid, good, and then methanol, ethanol, and then ethanoic acid. So these compounds are protic solvents, solvents that contain the hydroxy group and can also donate hydrogen bond to substrate. We call them protic solvents. So in terms of polarity, the polarity decreases as you go down, meaning that water is the most polar. And then here the least polar is ethanoic acid. Water, methanoic acid, methanol, ethanol, and then ethanoic acid. So you see they all contain the hydroxy group inside their structure, and then they can form hydrogen bonds. So that is it. And then any SN reaction, a nucleophilic reaction that involves these solvents is likely to occur, or most likely to occur, by SN1 reaction mechanism. So this is the 5th feature or characteristics of SN1 reaction mechanism. Then the 6th feature is it may involve racemization. So it may involve racemization if the central carbon is chiral. So what is racemization in organic chemistry? Is the process whereby an optical active compound or chiral molecule mixture converts into racemic mixture. So racemization is the process by which an optical active, or we can call it chiral molecule, converts into a racemic mixture. Converts into a racemic mixture. So what do you understand by the term racemic mixture? So in organic chemistry, racemic mixture is a mixture of equal amount of enantiomers of molecules. So a racemic mixture is a mixture of equal amount of compounds called enantiomers, which are optical isomers. So during SN1 reaction, if the product form is chiral, the final product form is chiral, it's going to form a racemic mixture that is going to produce two compounds that are mirror images to each other. Now, let me explain further what is meant by a chiral compound or optically active compound, which can undergo this process, which we call racemization. Now, for a compound to be chiral in organic chemistry, the carbon atom will be bonded to 3 different groups. You can see that? This central carbon is bonded to 4 different groups, R, Y, S, and Z. So this compound is marked asterisk. This is called a chiral compound. So such compound is said to be chiral in nature. Out of the 4 groups, 1, 2, 3, 4, none will be the same with each other, different from each other. So this compound is said to be chiral. So, and you're going to exhibit isomerism, whereby you have a mirror here, have another compound that looks like it, whereby these atoms, S and Y, will swap their position. Y comes to this position and S moves to that position. You see, these 2 compounds are mirror images to each other, and we'll call them enantiomers. Enantiomers. What it means is that if I should pull out, if it's possible to pull out this one out, pull it out straight and then merge it on this, the groups cannot merge. This Y will now be on the S position, S will now be on the Y position. That means the groups will not superimpose on each other. So we'll now say that mirror images to each other. So enantiomer. So such compound whereby the central carbon is bonded to 4 different groups are called optical active or chiral compounds. Now, what do you mean by racemic mixture? A racemic mixture is one that produces this kind of isomer, these 2 isomers in equal amount. 50% of this one and also 50% of that one. So in SN1 mechanism, we are very careful of stereochemistry. So if the compound produced as the final product has a central carbon that has 4 different groups bonded to it, it's going to produce its counterpart, its enantiomer, in equal amount. That is what is meant by racemization. And that is what a key feature of SN1 mechanism. But mind you that if the compound produced is not chiral in SN1 mechanism, it will not undergo this process. We will not only have 1 product. So we're going to have these 2 products if the compound produced is chiral that contains central carbon bonded to 4 different groups. And mind you, in organic chemistry, carbon is not the only chiral element that can form chiral element that can form chiral compound. Elements like nitrogen and phosphorus can also be at the center to form a chiral compound. Now, an example we have to demonstrate chiral compound is lactic acid. Lactic acid. I have the formula. have a carbon atom here. We have under have the carboxyl group up, have the hydroxyl group on one side, and then we have the methyl group, and then hydrogen group. This is our lactic acid, a three-dimensional structure of lactic acid. So, having done that, so you can see the central carbon. This is charismatically active because these four groups, you can see them, group 1, are all 2, 3, and 4 are all different from each other. So, if to get the enantiomer to have this structure, whereby this position will change, will swerve. We now have OH this side and methyl on this side. And then on the other side, we have hydrogen, while this will retain its configuration, COOH. So these two, see, look at them very well. So this is a mirror image of this. Draw this one out, pull it out from the board and merge it. So that this side will go into this side, while this side will go into this side. So you can't superimpose the imposition. So they are enantiomers. And when they're produced in equal amount during a chemical reaction, when I say that we'll have racemization taking place, we'll have a racemic mixture. So, having done that, we're now going to take an example of SN2 reaction, SN1 reaction, SN1 reaction, and then look at the making of the reaction. So, an example is reaction between 2-bromo, 2-methylpropane, and methanol. 2-bromo, 2-methylpropane reacting with methanol. So this reaction is an SN1 mechanism. So let's explain why it will involve SN1 mechanism before we go to the mechanism of the reaction. We'll explain because you have to know how to define whether the reaction is going to go by SN1 or by SN2, because in examination somebody may not ask you to give you the mechanism. Will tell you yes, it occurs by nucleophilic substitution reaction. Then you have to predict and then explain the mechanisms. You're going to know the one that will involve SN1 and the one that will involve SN2. When we did SN2, I told you that SN2 mechanism normally involve either methyl halides or primary or 1-degree alkyl halides. And in the presence of some solvents, which I mentioned, those solvents include dimethyl sulfoxide, I also mentioned acetone, I also mentioned some other solvents that are necessary for SN2 mechanism like diethyl ether, and I call them aprotic solvents. Now, going to SN1 mechanism, I told you that you make use of protic solvents. And if you look at the board, methanol is one of the protic solvents we have. I mentioned water, I mentioned low molecular weight alkanol, like methanol is an alkanol. I mentioned ethanol, I also mentioned methanoic acid. Those ones are protic solvent. Now, this reaction appears to take place by SN1 because we have a protic solvent here. Then we have to look at the structure of the alkyl halide to know whether it's tertiary or it is because we said that SN1 mechanism occur mainly in the presence of tertiary alkyl halide. So let's look at this structure. Propane is 3 carbon. You can see that. So 2 bromine, there is bromine on number 2. They call this 1 and 2. Then 2 methyl means also there is methyl on number 2. So we can complete everything with hydrogen, H, 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 and H. So look at this compound. Let's clarify it into primary, secondary, or tertiary alkyl halide. And no. So if you look at this, the carbon bearing the halogen, we'll leave it without compressing it, as I described earlier in the video. We compress this one, that gives us CH3 linked to carbon, CH3, bromine, and CH3. So this is a 3-degree alkyl halide or tertiary because it contains 3 alkyl group, methyl groups, alkyl groups bonded to the carbon of the functional group or the bromo group. So this is a tertiary or 3-degree alkyl halide. So the reaction that will take place here will be by SN1 reaction mechanism. So having done that, we can now proceed to illustrate the mechanism of this SN1 reaction mechanism. So step one, before we go ahead, let's see draw the structure that will help us. Okay, this step one is the generation or production of the carbocation. Because I told you that in SN1 mechanism, carbocations are produced. So remember the structure of the compound. Compound is like this: CH3, C, CH3, CH3, bromine. So we're going to draw the three-dimensional structure of the compound. So carbon, if you see the central carbon, if you see it here, then this one, bring this one up, the methyl group. Then the bromo, the representative atom, will be on the right-hand side, because the leaving group. Then this other group, one go with the dotted line, and then one goes with the wedge. So the bond will go straight to carbon. So, okay, that is it. So we have drawn the structure, you can examine it. One carbon, CH3 group, there are three. 1, 2, 3, and then bromine there. So having drawn the three-dimensional structure of this compound, what else do we do? The next we're going to do is to generate the carbocation. Remember, there are two electrons shared to form a single bond. And to generate a carbocation, this is the slow step or the rate timing step. This bromine atom will leave with the two electrons, leaving this carbon to become positively charged. So now I have CH3, then CH3, then the wedge to the methyl group, and then positive, this is the carbocation generated, and then the bromine or bromine ion departs with excess electron. So that's the first step in the reaction. Generation of the carbocation is of paramount importance. So we have that produce. Then that's the first stage. So we can still redraw the carbocation because the carbocation has a planar shape. So we have to draw it in a proper way. Being planar, we'll have the methyl group will be here. Then that the actual shape corrected. So planar in nature. So that is the carbocation generated in the reaction. So the next step now will now involve reaction of the carbocation with methanol. So the carbocation intermediate form will now react with the nucleophile, which is methanol. So we'll move on. Step 2. Methanol reacts on either side of the carbocation intermediate. So methanol attacks either side, both sides of the carbocation intermediate. Okay, to give what we call ozone ion, to give ozonium ion. So we'll draw the carbocation we generate in the reaction. CH3 with positive charge. CH3, then the wedge, then CH3 here, produced here. So these are carbocation. So the methanol, which is the nucleophile, will now react with this on both sides. So of the carbocation. So this is methanol. Then CH3, methanol. So this is methanol, CH3OH. So I can say the bond, put the hydrogen down there, that's the better way of doing it. Then also the same methanol drawn this side. I say it react on both sides. So have this same methanol. Remember that the carbon atom is electron efficient. So there's no atom on the carbon that will repair the methanol, unlike in SN2 mechanism. So this methanol can fix itself here or fix itself there. So we have two possible structures of the product or ozonium ion produced. And this is the first step. The first step. So when this reaction occurs, we now produce, from the back attack, we're going to have this CH3, the methanol. Okay, the electron will now have only one pair of a lone pair remaining on oxygen. Why this one used to form a bond with this? So we'll draw a bond, and then we'll have this, have CH3, then CH3 again, the wedge for the other methyl group, CH3, and then we're going to give this carbon, the oxygen, the positive charge, because the oxygen appears to be losing the electron to the carbon, making the carbon electron rich. So that the first ozonium ion produced. So I should be drawn better this way. Okay. And then hydrogen. All of them on one side. So that's it. That is when you have a back attack. You look like this. Then when the attack comes from the front of the carbon, we have another structure that is somehow different, but similar to the first one anyway. So we now have this. We draw it here to create a space. So it should be plus. So there, because of no space, let me put it here. When I have this, the methyl group. Then this is I think this should be CH3. So here should be CH3, please, as well. So CH3, not H. So that is it. That's the right structure because there are two methyl group. Move to one side. So I have this also. The same structure, CH3. But this time around, this part moves to the right hand side since the methanol is attacking. So methanol will be on the left hand side, attacking from the front. So now have a bond created here, and then we now have the methanol attaching itself. You see that? And this place becomes, the oxygen becomes partially positive because it's losing electron. So you can look at this structure. You can look at this structure drawn here. And this. So this is plus this. That the same, except from the arrangement. So in this one now, this part on the right hand side appear on the left hand side. While this part on the left hand side now appear on the right hand side. The same kind of structure. So it means that the methanol can attack from the rear, from the back, to give you this kind of structure. And then if you attack from the front, it now look like this. So this plus that. So that is the second step of the reaction. We now go to the third step of the reaction. The third step is, or step 3, is that we have a proton transfer from the ozonium ion to the methanol or solvent. So step 3 is proton transfer from the from the ozonium ion that this intermediate formed to the methanol, that is solvent or the nucleophile. So have that. That is step 3. So we're going to draw any of these, either this one or that one. You take any of them because each of them represent the ozonium ion, where the oxygen atom there has a positive charge. So you draw any one of your own choice. So perhaps let's use any one. Let's use this one. You draw it. Have this CH3, then that. Only emphasize that the bond goes from carbon to carbon. So CH3, So then that is the structure we have there. The lone pair, hydrogen, and then CH3. So this is the oxygen ion. So one of them taken now for the final reaction. Then plus the methanol. It's still a methanol. So H and then CH3. So there's going to be a proton transfer from this ion to the methanol. Proton means hydrogen ion without any electron. This is just remove hydrogen ion here and move it to the lone pair here. And then these two electrons, this is a single bond, is returned back to oxygen. So now I have a final product as CH3, then CH3, then the wedge for CH3 again, that is this. Then we now have O, oxygen, then CH3, that the lone pair here already up, and that lone pair, then the positive charge vanished because this is not electron rich. So having done that, we now have this one produced as well. Oxygen, hydrogen, this lone pair that is on top. This lone pair here then forms a bond with hydrogen. So you can see that. Then CH3. So you have that, and then this becomes positively charged because it has appeared to have shared electron with hydrogen. So that's the final product. And the final product is called, so the final product is called 2-methoxy-2-methylpropane. 2-methoxy-2-methylpropane. That is the name of the final, the IUPAC name of the final product. Why is it 2-methoxy-2-methylpropane? You can draw the structure very well and then know why it is called 2-methoxy-2-methylpropane. So let's look at the structure. There are 4 carbon atoms here. The longest, as a beginner, I may not name it for, the longest chain is one carbon chain, 1, 2, 3, or 1, 2, 3. Anyhow I want to name it, 1, 2, 3. So you can draw it, open it up. This is 3 carbon in the straight chain. I cannot say 1, 2, 3, 4. No bond join this to this. So I find the longest carbon skeleton, 1, 2, 3. So I cannot say move and say 1, 2, 3, 4 because also it's not carbon. So it's 1, 2, 3, or 1, 2, 3, or 1, 2, 3. It's still 3. So now this carbon number 1, carbon number 2, carbon number 3. On carbon number 2, you have a group here that is joined to it. This is the methyl group. So methyl group is on number 2. On the same carbon number 2, you have this group OCH3, which is called the methoxy group. You can see that. So you have it. So 1, 2, 3 form the straight chain. Then on this carbon, you have methyl group and also have a methoxy group on carbon number 2. Then you fill up this place with hydrogen. So the same compound as you have there. So then the compound 1, 2, 3, or that way 1, 2, 3, 2-methyl, 2-methoxy, 2-methyl, then propane. So that is the compound we have on the board there. That's the final product. Then we say that in SN1 mechanism, that the final product can lead to racemization, that is giving you 2 enantiomers or 2 isomers of the same compound, the racing mixture. So, but it's not a must. Is this compound chiral? This will lead to racemization if this compound is chiral, but this compound is not chiral. What am I not being chiral? Look at the central carbon, which is this one. Let's look at the group bonded to it. CH3, OCH3, then CH3 if I compare this side, and also CH3. There are 4 groups attached to the central carbon. 1, 2, 3, 4. And out of the 4 groups, 3 are the same. So you cannot say that this compound is chiral, it's not optically active. Because if the four of them were different from each other, we would have been talking about chiral compound. Then we'll talk about have the racemic mixture. So we only have one product here. We're not going to have anything like racemic mixture in this kind of reaction. Had it been that this compound form is a chiral compound, we're talking about having two isomers of this produced in racemic mixture. So we'll have only one product produced in this reaction. So having done that, we'll now go over to another thing, another aspect of this topic. We'll now discuss the factors affecting, or before we go to the factors, okay, factors affecting SN1 and SN2 reaction mechanism. So the first factor that affects SN1 and SN2 reaction is what we call nucleophilicity. And this factor is a kinetic factor. So it says the kinetic property and deals with the ability of the nucleophile to donate electrons to form bond with the substrate and displace the leaving group. It plays predominant role only in SN2 mechanism, since nucleophiles do not participate in the rate determining step of SN1 mechanism. So this factor plays role only in SN2 mechanism, because in SN2 mechanism, the rate of reaction depends on the constitution of the substrate and that of the nucleophile. So that's why the type of nucleophile or the structure of nucleophile plays predominant role in determining SN2 reactions. But in SN1 reactions, the nucleophile is not found in the rate determining step. So the type of nucleophile involved in the reaction has no role to play in SN1 mechanism. So in terms of effectiveness of nucleophiles to bond with the substrate or to displace the leading group, we can classify nucleophiles into good, terms of effectiveness. We have good nucleophiles, we have moderate nucleophiles, we also have poor nucleophiles. So the better the nucleophile is, the better it can, the faster for it to displace a leaving group. The good nucleophiles include the halide iodide, the bromide ion, the iodide ion. These are good nucleophiles. Also the methyl thiolate ion. I don't know the name of this ion. Then the alkyl thiolate ion, alkyl. So the S minus is called thiolate ion. Then the hydroxyl ion or hydrogen ion, OH or HO, negative goes to oxygen. Then have other example like the methoxide ion, and then methoxide ion, and generally the alkoxide ion, which is an example of it. These alkoxide ions. Methoxide is a kind of alkoxide ion, methoxide ion. So these are classified as good or effective, most effective nucleophiles in SN2 reactions. We also have moderate nucleophiles. Moderate include the carboxylate ion, or this is called ethanoate ion, which is a kind of carboxylate ion from ethanoic acid, organic acid. Then we also have the carboxylate generally, which this is a special kind, carboxylate ion. So this is a kind of carboxylate ion. So ions from organic acid. We have the thiol. Okay, RSH, pronounced thiol. So we have the dialkyl sulfide. Dialkyl sulfide, because this is dialkyl, two alkyl groups. There we have the primary amine. Primary amine, NH2 is amino group. Primary amine. We have the secondary amine and the tertiary amine. Secondary amine, and then the third degree or tertiary amine. So these are moderate leaving groups, moderate nucleophiles, sorry, that can also have good effect on SN2 reactions. So we have also the poor living groups, the poor groups. So it have effect in the poor living groups, sorry, the poor nucleophiles, sorry, not living, the poor nucleophile. The molecule considered poor nucleophile include water, ethanol. These are poor nucleophiles, not good at all. That's why they're only found in many in SN1 reactions. Alkanols in general, this is your formula of monohydrate alkanols, ethanoic acid. So these ones are classified as poor nucleophiles and found mainly in SN1 mechanism, and then generally alkanoic acids. So these are poor nucleophiles. So go to the second property, that second factor that affects nucleophilic reaction, which is a structure of the alkyl halide. Structure of the alkyl, number 2 property, structure of the alkyl halide. So number 2, which we are discussing today, structure of the alkyl halide, also is a factor that govern SN1 and SN2 mechanism. As I told you initially, that I said that SN2 is favored by methyl halides and primary or 1 degree alkyl halides or halalkenes. So these are the kind of compound that undergo SN2 reaction, while SN1 is favored by only 3 degree or tertiary alkyl halides. So that today. Then I say that for secondary alkyl halide, 2 degree alkyl halides or tertiary secondary alkyl halides can go by either SN1 or SN2 depending on the type of solvent and nucleophile. So if the solvent is an aprotic solvent, aprotic solvents are things like, so I say, like dimethyl sulfoxide, diethyl ether, acetone or propanone. Then that reaction will go by, that secondary alkyl halide will go by SN2 mechanism. But if the solvent is a protic solvent, just like methanol, water, organic acid, then that reaction will go by SN1. That reaction with a secondary alkyl will now go by SN1 mechanism. Now, number 2 factor. Then, number 3 factor is the living group. The living group. So, the living group, we said here that the ability of a group to function as a living group is related to how stable it is as an anion. So the ability of a compound of a group started to function as a living group related to how stable it is as an anion. Anion means negative ion. Negative ion. The most stable anions and the best living groups are the conjugate bases or strong acids. So how some of the living groups atomize for you on the board in terms of their decreasing stability or stability. So you have iodide ion greater than the bromide ion, chloride ion, which is far greater than fluoride ion. Fluoride is better than ethanoic ion, greater than hydroxide ion, methoxide ion, and then amino ion. You look at this arrangement, the best living groups are iodide, bromide, and chloride ion, while the poor or the worst living group are hydroxide, methoxide, and amino ion, fluoride and ethanol ion are considered as being, okay, fluoride, this is not ethanol, this is fluoride and yeah, ethanol ion, yeah, good. Fluoride are considered as being moderate leaving groups. So that is it. So this group will easily leave when a nucleophile approaches. They can easily be displaced than these other groups over there. So the next one is type of solvent. The next factor that affects SN1 and SN2 mechanism is the kind of solvent or type of solvent. Solvents play an important role because they help to solvate the substrate and also solvate the anion or the living group. So we have two kinds of solvent which we mentioned today. We have the protic solvents. We also have the aprotic solvents. So these are very important in SN1 and SN2 mechanism. So the protic solvents are required mainly for SN1 mechanism because they solvate the carbocation produced in SN1 mechanism and the leaving anion. So they help to stabilize the carbocation. So we call them the protic solvent. So they have or possess the hydroxyl group and form hydrogen bonds. So as we listed before, they include water and then low molecular weight with organic acid and alkanols, methanoic acid, methanol, and then ethanol, and then ethanoic acid. So this is their list in decreasing polarity. So decreasing polarity. Water is the most polar here. So, and then why this one is the least polar. So as you move down, you see that the polarity decreases. Water being the most polar, and then the acid being the least polar in that classification. And then look at those reagents. So any reaction that might involve any of these reagents will always occur by SN1 mechanism. So we call them the protic solvents. Then for SN2 mechanism, we'll use the aprotic solvents. So these solvents, they do not solvate the carbocation. So, or neither do they solvate the anion, anion or living group. So they lack the hydroxyl group and do not form hydrogen bonds. So we have these ones. So examples are dimethyl sulfur oxide, CH3, 2 methyl group, then sulfur oxide at the middle, dimethyl sulfur oxide. Another example of this kind of ion is acetone. Of this kind of solvent is acetone. Otherwise, it's called propanone, CH3, COCH3. Then we have also dichloromethane, CH2Cl2, and then we have the diethyl ether. So these solvents are considered as being aprotic. So they do not form hydrogen bond. And then also as you go down, they have decreasing polarity. So they don't form hydrogen bond and they don't have hydroxyl group, and they're required mainly for SN2 mechanism. So these are key things for you to know when the reaction is occurring by SN1 or by SN2. When you encounter this solvent, basically it's SN1. Carbocation is formed and it involves two steps. When you encounter these cations, these solvents is mainly by SN2, and then it's a concerted reaction whereby it involves a single step. You don't produce any carbocation. So we'll now go to differences between SN1 and SN2 reaction mechanism. The differences. So look at the differences between SN1 and SN2 reaction mechanism. or reactions. The first is mechanism. SN1 is stepwise. It involves two steps. SN2 is constructed. It involves a single or one step. Number two, rate determining step. SN1 depends on substrate only, the formation of carbocation. SN2 depends on nucleophile and substrate. Number three, reaction order. SN1 is first order. Look at the rate equation for the rate determining step. Rate equal to rate constant multiplied by substrate. So the power of the substrate is only 1 here. That is first order reaction. While SN2 is second order reaction, the rate equal to rate constant multiplied by the substrate concentration, then multiplied by the nucleophile concentration. The power is 1, 1 each. So 1 plus 1 gives you 2. That is the second order of bimolecular reaction. Then number 4, substrate preference. SN1 favor tertiary or third degree alkyl halides, as we explained in our teaching. Then SN2, that is SN2 favors methyl halides and primary or 1 degree alkyl halides. Then stoichiometry of the product. SN1 can lead to racemization, that if the central carbon is chiral, and then SN2 leads to Warden inversion of configuration. So these are the differences. We still have 2 more differences between SN1 and SN2 reactions. 2 more differences. Number 6, that is solvent. SN1 prefers polar protisolvents, as we discussed. Polar solvents like water, low molecular weight alkanols, ethanol, methanol, and low molecular weight organic acids like methanoic acid and ethanoic acid. Then SN2 prefers polar aprotic solvents. Aprotic solvents like dimethyl sulfur oxide, acetone, diethyl ether, and so on. Then number 7, carbocation formation. SN2 forms carbocation intermediate. So SN1 forms carbocation intermediate, while SN2 does not form carbocation intermediate. So, having done that, we discuss that SN1 reaction can lead to racemization, which we discussed today. Racing mixture is a mixture of 2 enantiomers in equal proportion. Before we're going to take an example of an SN1 reaction that will involve racemic mixture in the final product. And for you to have a racemic mixture in the final product, that means the final product must be a chiral molecule. I have explained what is meant by chiral molecule. A molecule that has a central carbon linked to 4 different groups. So before we go ahead, we're going to learn how to name chiral molecules according to a system given by what's called CIP system. So that CIP is given by 3 different gentlemen, which include Kahn, Ingold, and Prelog. So Kahn for the first letter, Ingold second letter, and then Prelog. So system of naming chiral molecules. So molecules. So these 3 gentlemen provided a system of naming chiral molecules. They use what's called R enantiomer. The R enantiomer. They name the isomers using R and S configuration. R enantiomer and S enantiomer. The word R means rectus. Rectus means that is a Latin word meaning clockwise direction. And then they also use S. S means sinister. And sinister in Latin word means counterclockwise or anti-clockwise. So in naming 2 enantiomers obtained from a chiral molecule, we have a rectus, and then we have a R, and then we also have the S enantiomer called sinister enantiomer. So we're going to take an example and then explain how this works out. So you look at these 2 structures on the board. that are isomers to each other, or the enantiomers, optical active. So why do they say the optical active? Because the carbon atom at the middle is chiral. The four groups bonding the carbon atoms are different from each other. Fluorine, bromine, chlorine, hydrogen are different from, that is the chiral compound. So this compound can exhibit optical activity. So it's an optical compound. So this, and they look at them very well. They are enantiomers. They are isomers to each other. They are mirror images, because if you look at the hydrogen and chlorine on this side, on the left-hand side of the plane, have been transformed to the right-hand side, while bromine on the right-hand side here have been transformed to the left-hand side. So you see the isomer to each other. This is called the R enantiomer, and this is called the S enantiomer. Now let's look at the CIP system. Why we call this the R enantiomer? So according to these gentlemen, Kahn, Ingold, and Prelog, in this system of naming, we have the atoms, you find the atomic numbers. The number of bromine is 35, chlorine is 17, hydrogen is 1, and then fluorine is 19. Now, this system is taken, or the compound is named in priority of decreasing atomic number. That is from the highest atomic number to the lowest atomic number. So the highest among this is bromine, is given number 1. Followed by 9, not 19. Followed by chlorine, which is number 2, being 17. The next is fluorine, which is this 35, 17, number 3. And then the least is hydrogen, number 1. Atom number 4, we give number 4. I repeat, the atoms are numbered in order of their decreasing atomic number. So this is number 1, number 35, number 2, 17, then number 3, the atom number is 9, and then number 4, which is hydrogen. Atom number is 1. This atomic number is that. So having done that, if you see the movement, we want to move from number 1 to number 3. We have to follow this way, this order. 1 to 3. That is in a clockwise manner. Moving from number 1 to number 3. So that's why this is called the R enantiomer of this compound. So rectus, clockwise. If you go to the other structure, if you number this, number 1 being the highest in atomic number, number 2, 17, number 4, number 3, sorry, and then number 4. So number 35, 17, 9, and 1. So to move from number 1 to 3, we have to move all in this direction. That is counter or anti-clockwise. So you see, that why it's called sinister enantiomer, in opposite way. So clockwise and then anti-clockwise. R enantiomer and S enantiomer of the compound. So you can see that. So this is their system of nomenclature, how to name the enantiomers with the R and S convention, which we call the CIP, Kahn, Ingold, and Prelog system. So take another example. The second example I have on the whiteboard is lactic acid, showing the R and S convention using the CIP system of naming. So let's look at it very well and see why we call the one on the left hand side the R, lactic acid, enantiomer, and the one on the right hand side the S, lactic acid, enantiomer. So if you go by CIP system, the oxygen here, consider the first element bonded to the carbon. The oxygen here, atom number of oxygen is 8. Carbon is bonded to the carbon. The atom number of carbon is 6. Hydrogen is the least, 1. This carbon here is also the same 6. In this, we have two elements that have the same atom number. That is this one, carbon here and carbon here. We have also going to untie these two. So carbon is having 6, carbon is also having 6. So what do we do? In a situation whereby you have two elements bonded to the chiral carbon, and the two elements, two groups starting with the same element, carbon, in this case, carbon, what do? We'll consider the second element. Second element is oxygen, which is 8. The number is 8. while this one, the square element is here is 1. So this one has a higher magnitude than hydrogen. So this is considered before this. So I come again. In a situation whereby you have two groups attached to the central carbon, chiral carbon, and those two groups start with the same element bonded to the same carbon. Carbon in this case, also carbon in the other case. You now go to the square element. The square element, what you consider, this is 8, and this is atomic number of 1. So this one has a higher atomic number than this. So we'll consider this one in preference to this. So this hydroxylase number 1, also being the highest in mass atomic number. This is number 2 because the oxygen at the second oxygen is more than hydrogen, has higher atomic number than hydrogen. This is number 4. Number is small, while this one now comes out number 3. So let's consider the movement now. So when you move, you see that from moving from 1, from the highest to the from 1 to 4, we move like this. We must pass through 2 before we come to, even though there's 4 in between. So this is a clockwise movement or motion. So it's called lactic acid. In this situation now, in this other example, these are number 4. This is our number 2 from the same membrane. These are number 1. These are number 3. Moving from 1, this is number 3. From 1 to 4, or 1 to, as the case may be, you don't have to move from 1 to 3. You must move through the order 1, 2, and pass 2 before coming to 4, or the direction. This is anti-clockwise. So that why it's called S-lactic acid. So moving clockwise, rectus. Moving anti-clockwise, opposite. Sinister, counter-clockwise direction. So having done that, we're going to take an example of a reaction now that will involve producing a chiral compound or giving out a racemic mission. So look at the reaction on the board. We are asked to predict and illustrate the mechanism of the nucleophilic substitution reaction given below. You see that compound given to you there, which is 2-chlorobutane with methanol. And we are asked to predict of which of the mechanisms, is it SN1 or SN2 reaction mechanism. First of all, we can look at the nature of the alkyl halide. Look at the nature of the alkyl halide. You see that this alkyl halide is a secondary alkyl halide. I can compress this. This is C2H5. 2 alkyl groups linked to the carbon carrying the halide, the halogen group. So the secondary alkyl halide. And I told you that 2-degree alkyl halide can take place by either primary or by either SN1 or SN2 mechanism. So we cannot actually say it's SN1 or SN2. Before we conclude that it's SN1 or SN2, we have to consider the nature of the solvent. Look at the solvent used, methanol. This solvent is a polar protic solvent. And protic solvents are only used in SN1 mechanism. So this reaction will take place by SN1 mechanism. So the prediction will occur by SN1 mechanism. So the first thing we're going to do is we're going to first of all show the mechanism by step by step. Because SN1 reaction mechanism occurs in 2 steps. So the first step is nothing but the formation of the carbocation. So step 1 is formation of carbocation intermediate. So that's the first thing to happen here. So we're going to draw the three-dimensional structure of that compound. So that will give us this CH3 here. Then the chlorine atom, halogen leaving group will be on the other side. Then I have hydrogen there. I have a wedge for the other group. So you can see it's the same compound, 1 carbon, chlorine, hydrogen, and then we have that. So then what happens is the slow step is formation of the carbocation, whereby this chlorine pulls away these 2 electrons that is being shared with itself and carbon. So you now produce a carbocation, so which has a planar shape. So that is the carbocation produced. You draw the planar structure, has a positive charge, while the chloride ion leaves with 2 electrons being negatively charged. So this is the carbocation produced. So that's the first step of the reaction, carbocation formation. Second step is now that the carbocation will now react with the solvent. There is here nucleophile methanol. So step 2 is carbocation reacts or is attacked by the nucleophile, which is methanol. So you now have the methanol molecule. You can draw the structure here. So this is your methanol. So CH3. Then attacking the carbocation front and back. So have it. This is the carbocation produced. The same structure we have above. So positive. So the attack can be on either side of the carbocation I will explain in the reaction today or in this video. So this one can attack this point. This one can still attack this point to give us 2 products, 2 ozonium ions. So we're going to produce 2 products here on the other side of the board. We're going to have this product, maybe perhaps we're going to have oxygen CH3, then hydrogen, a lone pair here. One of the lone pairs will be used to form a bond with the carbon atom. So you see it, CH3, then C2H5, and then hydrogen, and then the C2H5 with the wedge formed. So the positive charge now will now go to oxygen that appear to have been losing the 20 electron to the carbon atom. So this is one of the products we expect, one of the ozonium ion that we expect. Then the next one also is, this is when we have a back attack. This is formed. Then when we have a front attack from this side, we'll draw this part first. So CH3, then hydrogen, C2H5, then bond to the solvent or the nucleophile. So have a lone pair of electrons. The same kind of structure produced again, but in version of a configuration. So you now have the ozonium ion produced. Then the next step now is that each one of the ozonium ion will now react again with the nucleophile with the ethanol again once more. That's step 3. So in step 3, so we now have the ozonium ion or proton, your abstraction of proton. Abstraction means removal or elimination or proton from the ozonium ion by the solvent or the nucleophile methanol. So we'll draw any of them of our own choice, this one or that one, anyone you want to draw. That's okay for you. So we'll draw one of them. So we'll have this CH3, then hydrogen, the wedge, C2H5, then oxygen, then hydrogen again here, CH3, and remember that the lone pair of electron already on the oxygen. Then we'll now draw the ethanol, which is the solvent or the nucleophile in this case. Then that is the ethanol. Good. So we're going to remove 1 proton from the ion. So this proton means hydrogen ion moves away and goes to one of the lone pair. Electron returns back to the oxygen. We now have this CH3, hydrogen at the final product, then C2H5, then we have this electron pair returns here, that's the electron returns here, then we have CH3, okay, then plus we'll have this, a bond formed. When this goes there, forms a bond with this electron, then H, CH3. So this is the final product. And the final product is called, the name of the final product, if I can name it here, is 2-methoxy 2-methylbutane. 2-methoxy 2-methylbutane. Okay, let me get it right. It's 2-methoxy butane. Look at it very well. 2-methoxy butane. Look at this is 2 carbon, 3, 4. 2, 3, and 4. You can see it. You can open this one if you want. There is 2 carbon. 1, 2 here, 3, and 4. Don't get change 4. So, and then link on this and this number 2 carbon now. Okay, to number it 2, 3, 4. But this is an substituent group, methoxy group. So the end that will give you the small number is from this end 1, 2, then 3, and 4. If you like, if you open this, these are like 2 carbon atoms. C2H5. The same thing. So C2H5. You're like this. So you have this 1, 2, 3, 4. So you have 4 carbon longer chain, and then on this number 2 you have the methoxy group. So this is 2-methoxy butane. So that's the name of the compound. Longer chain is 4 carbon, and then on number 2, the group attached is the methoxy group. So 2-methoxy butane. Okay, let's go back. Now this compound we have formed, is this compound chiral in nature? If the compound is chiral in nature, that means you're going to produce 2 more, you're going to give us a racemic mixture. Then look at it very well. Look at this structure very well. You see that if I draw it, 1, 2, 3, 4, butane, that is 4 carbon, 2-methoxy on number 2, I have OCH3. Then I fill it up with hydrogen. So 2, this is the structure, the same compound we've produced as the product. So the normal structure, to make it clearer to you. So we see is this compound chiral. So let's look at the carbon. Let's leave the carbon that contains the functional group, the methoxy group, and then compress this one, CH3, then CH, OCH3, and then C2H5. So this compound is chiral. It's a chiral compound because this carbon must be optically active. So it must give us a racing mixture. So the reaction will not end here. Because this compound we arrange to give us 2 products. Because what I say is chiral, because these 4 groups, 1, 2, 3, 4, are different from each other. So because they are different, this compound will exhibit optical activity. So it will lead to racemization, whereby we're going to produce 2 compounds from that product, 2 compounds that have a that exhibit chilarity, or racemic modification. So let's see how we're going to go about it. You look at this compound now very well produced. Let's look at the first element according to the CIP method. Oxygen bonded straight is atom number 8, carbon 6, hydrogen 1, and then this other one is carbon again, but also 6. But because this carbon is bonded to hydrogen, this it should be better. This is the right way because carbon bonds to carbon. So 6. So this carbon is highest magnitude. That will take this oxygen will take number 1 because it's highest atomic number. Then these 2 are competing. We'll have to untie them. So because this is bonded to hydrogen, the lower atomic number. This is bonded, and that carbon, the higher atomic number. So this one will take a higher number. This is carbon linked to carbon. The next carbon element is 6. Carbon linked to hydrogen. The next is 1. So this one takes a higher preference, a higher atomic number than this. So this will be number 1. This will be number 2. This will be number 4. While this one will be number 5. So you see that. So if I draw the 3-dimensional structure of this compound, I can have it this way. So I can have a hydrogen. Anyhow, hydrogen. I have the methyl group. I I can have the methoxy group. I can have a C2H5 group this side. So this is number 1. Atom number is 8, highest. Number 2 is 6, the same as this, but the second element to consider the second element, which is carbon, which also is higher than hydrogen, which is 1. So number 4, and then number, what again? Number 3. So that is it. I can still do it another way. Let's see whether we can get another structure, whereby I will now swap the position. Hydrogen also is kept maintained up to get the enantiomer C2H5, and then we'll swap this side. We'll have a CH3, and then OCH3. Number 1, number what again? This is number 3. This is number 4. This is number 2. So we're going to look at the movement and know the one that is going to be R enantiomer, and then we're going to be S enantiomer. So if you look at this one, if you want to move from 1 to 3 or 1 to 4, I'll follow this movement, passing through to 4, coming to 4, 4 coming to 4. So I must move 1 to 3, for instance. Let's move 1 to 3. So there's the position of the 4, the 1, 2, 3 position. And then for this one, if I want to move from 1 to 3, I'll move that is. This is 1, this is 2. So I can't move from 1 to 3 without passing through 2. So that will go like this. So this one is a clockwise movement. So this is now called the R enantiomer, or R2-methoxybutane. While this one is now, this is anti-clockwise. It's called the S or sinister enantiomer. Since you know the compound, you don't call it enantiomer, you call it R2-methoxybutane and R2-methoxybutane and S2-methoxybutane. So you can see the configuration and how to apply it. So you see that. We'll take one more example before we round up this lecture. So look at this last example that says, predict, I illustrate the mechanism of the nucleophilic reaction below. We have that compound, which is 1-bromo-2-methyl-propane reacting with sodium iodide in the presence of dimethyl sulfide. So the nucleophilic reaction, we have to know whether it's going to go by SN2 or SN1 mechanism. Let's look at the alkyl halide first. So this alkyl halide given to us is a primary or 1-degree alkyl halide. Look at it. Look at where the halide is, the halogen group, bromo group is. You can see that. So it is a 1-degree alkyl halide. Look at the full structure. The bromine is on number 1 carbon. So 1-bromo, that indicates that is primary alkyl halide. So, and you know that primary alkyl halide, as we said in this video, primary alkyl halides react by SN2 mechanism. SN2 mechanism, which is the single step or constructed mechanism. It doesn't form carbocation. And then another thing that will help us is look at this solvent, dimethyl sulfoxide. This dimethyl sulfoxide is an approach solvent. And approach solvents are normally used in SN2 mechanism. So this reaction will only occur by SN2 mechanism, not SN1 mechanism. So the first thing that will happen is that this reagent will ionize to produce our nucleophile, which is the iodide ion. So that's the nucleophile we have here for this reaction. So let's now illustrate the reaction. Very fast one. So this is a single step. So it's a single step reaction. It doesn't occur in 2 steps. So we're going to draw the structure of this compound, the 3-dimensional structure, which look like this: the central carbon, then the methyl group, CH3, there, then hydrogen coming down there, and then this hydrogen and that methyl group will go with a wedge, being a bulky group, and then this group again, CH2, and then Br. So that's the 3-dimensional structure of the compound. Then remember that in SN2 mechanism, SN2 making the reaction. The nucleophile will attack at the same time as this group, the leaving group is going out. So we bring the nucleophile on this side, this is the iodide ion, to attack a backside attack because it has similar charge as the leaving group. So it can attack from this side for minimized repulsion. So this group leaves, while this one fits itself. So we now have the transition state formed, or yeah, the transition state will be formed. We now have this CH3 here, and then hydrogen, then the CH3 also on this side, and then the iodide ion attaching itself with a broken line to show partial bond formation, negative D, and then this side, the bromine group also attracting itself with broken line going out to show bond breakage, partial bond cleavage or breakage. So this carbon becomes partially positive. So you see that is the way it goes. Then finally we'll have our final product. So our final product, now we're going to write it on top. Our final product, the bromine ion will now finally leave. We'll now have C, okay, CH3 here. We're going to have an inversion of configuration, that is the Walden inversion of configuration. So we'll now have this H, and then the wedge for the methyl group, and then we'll have this, the anion will combine itself, CH2 with the anion will combine on this side. The nucleophile will combine on this side, nucleophile please. So you see the final product. So look at the product and look at the reactant. Everything here appears to be on the other side. So we have an inversion of configuration. That is what's called the Walden inversion of configuration. So having done that, we have done justice to SN1 and SN2 reaction mechanism. So as you can see it on the board. So we are taking examples, taking the lecture from the beginning to the end. So I know you have any comments, you can send a comment, and then we're going to reply you. So we thank our subscribers all over the globe. So for those in high institutions and for those that are willing to learn courses or that are studying courses in organic chemistry or pharmaceutical chemistry or natural product chemistry. So this aspect is for you. So it help you to know more of chemistry and then understand the rudiments or the intricacies in organic chemistry. Organic reactions are very important. And then when we talk about organic reactions, you only understand organic reaction by going to the reaction mechanisms. So stay always connected. Share the video to somebody that is in need, to students in high institution. Share the video to someone that will understand. Because sometimes when you read from textbook, you may not fully get the full or grasp the full knowledge. In our next video, we're going to look at elimination reaction mechanisms. So we're going to look at the E1 and E2 mechanisms and also addition reactions and so on. So thank you for listening. Thank you for staying connected. Always remain connected to Best Science Brain. Share our videos, like our videos, and then comment. Thank you very much.